Welcome to The Explainer. Okay, today we are going on a highly structured visual journey of literally epic proportions. We're calling it the Cosmic Zoom Out. We're going to start right here on our home planet, looking at the ancient history buried deep beneath our feet. And then we'll literally zoom out, past our solar system, past the edges of our galaxy, all the way back to the absolute dawn of the universe, before finally returning back home to explore the theoretical death of our own sun. It is going to be a fascinating ride.
Okay, let's dive right into this. Here is our cosmic roadmap for today. We'll start with Earth and our solar system, check out some next-gen space tech, hunt for exoplanets, unravel the secrets of the early universe, and then finish up with a massive what-if scenario about the sun. Let's get to it.
Part 1. Earth and our solar system. Because, to really understand the sheer vastness of space, we first have to look closely at our immediate cosmic neighborhood.
The scale of Earth's history is just mind-blowing. We all know the Chicxulub asteroid famously wiped out the dinosaurs at year zero. But what's really fascinating is that the impact actually created this massive, porous, hot water underground haven that was perfectly suited for supporting new life. Now, previously, scientists thought this underground hydrothermal system lasted maybe 2 million years. But new evidence stretches that timeline all the way out to 8 million years. Think about that. That's 8 million years of a sustained, life-supporting environment born directly out of a mass extinction event. So the crucial point here is that Earth's history isn't just about what happened on the planet, but what happened to it from space. For instance, researchers are now proposing that gravitational tides from massive planetary flybys might have actually caused some of Earth's other unexplained mass extinctions. And it gets crazier. Over 100 million years ago, two neutron stars collided, creating a kilonova that literally rained long-lived elements right into our oceans. And we know this for sure because scientists found plutonium radioisotopes hidden inside a piece of ferromanganese rock pulled from the Pacific Ocean floor way back in 1976. And our interactions with the local neighborhood are only accelerating. Humanity is really stepping up right now. Japan is launching the MMX mission in late 2026 to finally decode the interior and origin of Mars's tiny moon Phobos. On top of that, we are actively planning to protect our growing footprint out in space. In fact, the Schweikart Prize was just awarded for a proposal to create a brand new network specifically designed for monitoring cosmic threats to our off-world infrastructure.
Which brings us to Part 2, next-gen space technology. Leaving our solar system behind requires some truly spectacular tools to help us travel deeper and see further than ever before. Just recently, Europe's new Ariane 6 rocket soared into orbit, nailing its 8th successful mission insertion in a row by deploying 36 satellites for Amazon's Leo constellation. Better launch capabilities are absolutely essential, for sure, but so is keeping humans healthy once they actually get up there. Astronomers have developed this groundbreaking new pharmaceutical production method that will allow astronauts on long missions to literally grow fresh plant-based medicine on demand. Self-sustaining medicine and heavy-lift rockets. These are the critical stepping stones for deep space travel.
Now, once we're out there, what exactly are we looking for? Well, to definitively answer the question, are we alone in the 2040s, astronomers are dreaming up some incredible next-generation tools. The WM Keck Institute is detailing the LIFE mission, which stands for Large Interferometer for Exoplanets, envisioning an entire swarm of telescopes. Meanwhile, scientists are pushing for the Habitable Worlds Observatory, or HWO, to adopt a highly advanced, high-resolution, near-IR spectroscopy capability to hunt for those extremely subtle signs of life.
But perhaps the most mind-bending technological proposal out there right now is the Solar Gravitational Lens, or SGL. Let me break this down because it's wild. Scientists want to literally use our own sun's gravity as a giant magnifying glass. By positioning a spacecraft at just the right distance, we could capture light bent by the sun to image extreme cosmic objects far, far beyond exoplanets. We are talking about mapping the actual surfaces of distant white dwarfs and black holes. Let's move to Part 3, the hunt for exoplanets. Now that we have the tools, let's zoom further out into the galaxy to examine the strange worlds we'll actually be looking for. Picture this. You're the grill master at the annual Family 4th of July barbecue, and you're sweating bullets over the grill in the sweltering heat. "This heat is killing me," you say. And your brother-in-law, an astronomy professor, slyly replies, "Well, try being an exoplanet." It's a funny, relatable thought, right? But it perfectly sets up the punishing, extreme conditions we are finding out there in the dark.
Now, what's really interesting about this is the scientific payoff to that BBQ analogy. Astronomers call these worlds hot Jupiters. These are massive exoplanets that endure intense, literal star-powered barbecue conditions simply because they orbit incredibly close to their host stars. I mean, they are practically being cooked alive by stellar radiation. Or, actually, let's look at another extreme scenario. Imagine it's the year 2158. You're a grad student on Mars, eating freeze-dried ramen, and you've been tasked with finding a true lava planet exoplanet less than 50 light-years away. Now, you might immediately think of Jupiter's moon Io, which is incredibly volcanic. But Io is heated by tidal forces from Jupiter's gravity. A true lava planet exoplanet is a totally different beast. It's a world where the volcanism is caused by extreme heat directly from its host star, creating a highly active, hydrogen-rich atmosphere. Part 4. Secrets of the Early Universe. Okay, let's leave those scorching worlds behind and zoom all the way out to the absolute edges of the observable infant cosmos. Consider the timeline of a massive star-forming galaxy known as Rebels 25. Astronomers recently discovered a huge reservoir of cold molecular gas there, which is the direct fuel for star formation. And because of a phenomenon called redshift, where the universe's rapid expansion stretches light out to redder wavelengths, looking at Rebels 25 is literally looking back in time. We are seeing this galaxy exactly as it was when the universe was at barely 5% of its current age. The other 95% is all subsequent cosmic expansion. And these massive discoveries are actively challenging our models of how quickly the early universe formed. First, we have a flickering quasar seen just 850 million years after the Big Bang, yet it already features a modern, flat, pancake-shaped accretion disk. There's no way it should have formed that fast. Second, a JWST discovery, a galaxy cluster from 10 billion years ago that is inexplicably mature, heavily developed, and actively undergoing mergers. The early universe was apparently organizing itself way faster and far more maturely than we ever theorized. And this forces us to rethink everything, including black holes. We're all taught that black holes form from the collapse of dying stars, right? But there is another theory. Primordial black holes. This theory suggests that matter collapsed in on itself immediately after the Big Bang. Researchers are now actively questioning if tiny asteroid-mass primordial black holes might actually be hiding right now in the cosmic gamma-ray glow, which could potentially account for the universe's missing dark matter. Before we shift gears for our grand finale, I have to highlight this visually poetic discovery. Astrophysicists have found what is likely the very first pair of sibling supernova remnants. You have the well-known Jellyfish Nebula, and right next to it, long hidden in its bright glare, a twin. And incredibly, the pair are visibly connected by this bright filament of gas. It's just a beautiful reminder of the interconnectedness of these massive cosmic events. All right, with that, we're going to break our zoom-out pattern and bring it all the way back home. Let's move to part 5. What if the sun stopped? This is a completely fascinating theoretical thought experiment about the death of our own star. 100,000 years. Just let that massive number sink in for a second. If fusion inside the sun suddenly stopped today, we wouldn't even notice for a very, very long time. And that's because of what physicists call the photon traffic jam. A photon born in the sun's core takes around 100,000 years to fight its way to the surface. It bounces around in such a wildly inefficient random walk that the sunlight warming your face today was actually created before human civilization even existed. Our sun's surface is essentially 100 millennia delayed broadcast. This photon traffic gem brilliantly illustrates the Kelvin-Helmholtz mechanism. Back in the 19th century, two aristocrats, Helmholtz and Lord Kelvin, mostly by accident, figured out how the sun could theoretically keep shining even if its fusion furnace was completely switched off. It all comes down to a strange, self-regulating thermostat of hydrostatic equilibrium. Basically, the sun would just coast on its massive amount of stored heat. As it cools, it slowly shrinks, and that gravitational shrinking generates even more heat. So what exactly would happen in a scenario where fusion is just magically turned off? Let's walk through the exact chronological steps. Step 1, the neutrinos give the whole thing away in just 8 minutes. Since they don't interact with matter, they escape the core immediately, and scientists on Earth would instantly notice the neutrino drop. But step 2 is the terrifying part. For 10,000 years, to human eyes, nothing appears to change because of that photon traffic jam. Finally, step 3. The sun begins a slow, strange death, shrinking, briefly brightening, and coasting on that gravitational heat for tens of millions of years.
Which brings us to our final thought today. If the sunlight warming your face right now began its journey before human civilization even existed, what other delayed cosmic broadcasts are out there, quietly washing over us, just waiting to be decoded? Our universe is a massive archive of deep time, and as our journey showed today, we are only just beginning to build the tools to read it. Keep looking up, stay curious, and thank you so much for joining me on this explainer.